All right, let's get started. So do we have any questions before we get going today? All good? All right, so to continue where we were last time, we had a system A2 y double dot plus A1 y dot plus A0 y is equal to B0 u. And we want to try and find y as a function of time, right? Which we got last time to be inverse Laplace transform of B0 over A2 s squared plus A1 s plus A0 times u of s, right? And then we also had our other terms with the initial conditions, which we're not going to worry about for today, or at least not at the beginning here of this. All right, so just to continue and wrap up this example really quickly, right? Let's find y at t with A0 is equal to 12, A1 is equal to 10, A2 is equal to 2, B0 is equal to 1. Our initial conditions are 0 for both of them. And let's say u of s is equal to 2 over s. This is a step with a magnitude of 2, right? So just as kind of like a refresher from last time, we kind of already covered this, so we're probably not going to go through the entire step-by-step solution process here. How would you go about solving this? And we kind of did this last time already, so we can just talk it through very briefly here.
So was that supposed to be find y/s?
Y/t, right? Y/t, the inverse Laplace transform is what we have there, right? So we're looking for y/t where u of t was a constant 2, which is a Laplace transform of 2 over s. So how will we go about solving this? Break it down for me step by step. We're partial fraction expansion, right? So the first thing that we would probably do, even before we get there, just to be fully complete, is to plug in what u of s is to this, right? So we would plug in a 2 over s for this, right? Now, if we want to do partial fraction expansion here, how are we going to approach that? Probably something else we could do here that may help you guys out a lot is plug in our actual numbers, right? So B0 is 1, A2 is 2, S squared, A1 is 10 times S plus 12. And then this is all going to be multiplied by an S. And then that B0 is multiplied by the 2 up there, right? So how can we do partial fraction expansion with what we got here? Are we ready to do partial fraction expansion with the equations that we have here?
No, you need to rewrite the side bracket.
Okay, what do you mean by recognizable form?
In a form you can partial fraction.
Which would look like what? What are we looking for? Input and output, not quite. Factor it, right? We're looking for the roots, right? So what is the factorized form of the stuff on the bottom? We can leave the s on its own, right? And so we only have 2s squared plus 10s plus 12, right? We're going to factor that. How many potential solutions would that have? 2s squared plus 10s plus 12 is equal to 0. That's how we can find our roots for this, right? We're going to have 2, right? So it's going to be s plus something and s plus something else. Right?
And pull out a 2. So it'd be 2s, s plus
2s, s plus 3, s plus 2. What do you guys think? Yes, no? All right. 2, 3, and then you said pull out that 2 in the front, right? We would have ended up with s squared plus 5s plus 6, right? Is equal to 0 here. Now we're ready to do partial fraction expansion. Actually, those 2's on the top and the bottom will cancel out, right? So we could rewrite this as, I know you guys like to use A's and B's and C's, right? I'm just going to use constant C1, C2, and C3, where C1, C2, and C3 were solved using partial fraction expansion, right? Normally we go through and we'd actually crunch out what those numbers are, right? We don't need to worry too much about it in this particular case here, right? So once we do that, we can do our inverse Laplace transform here, right? For each one of these separate elements. Right? Because that's something that we can do with inverse Laplace transforms. We can separate them if we have cases of addition and subtraction. Right? And so from last time, we know what these are going to look like here. Inverse Laplace transform of C1 over S. What's that going to be? How about folks online? What is the inverse Laplace transform? What is this part? Folks online. There's a little bit of a lag, so we're going to need to be patient with them. You can hear me, right? Just C1, right? C1, yeah, unit step, which is just a constant here. That'd be a unit step would be if C1 was a constant of 1, right? What about for the second piece? Let's go with the folks in class. What is that going to end up being? Say again. C2e to the negative 2e, right? And then the third part will be C3e to the negative 3 times t, right? We've gone through that before. That's how we could solve this, right? Now, what if I only asked for y steady state or y at t approaching infinity, right? All the way back up here at the top, right? We could go through and solve this entire equation and then plug in t as a limit of t approaches infinity, right? To this equation here, right? But there'd be a faster way where we wouldn't have to go through all these steps here if we just want the steady state value. What is that faster way? What's that? Final value theorem, right? What does the final value theorem state? Y at t approaching infinity, or let's just say y steady state, right, is going to be the limit of s approaching 0, right, of s times big Y of s, right? Big Y of s was all this stuff in here, right? So, or let's go with actually this one right here. So plugging this in to the final value theorem, we're going to have a 2, we're going to have s times 2s squared plus 10s plus 12, right? And then we had an s on the outside here. We could figure out what this is going to be just by evaluating this using the final value theorem. So what do we end up being with the steady state value being in this case? Oh, and that s, very importantly, should be on the insides of these brackets here. So what do we end up with? What is our final value? What is our steady state value for y for this case of u? Right? The s here and the s here cancel out. Then we plug in s is equal to 0 here and here. These two things disappear. We end up with 2 over 12 or 1 over 6. Right? Exactly. Right? And so if we're looking for a steady state value and we already have a Laplace transform of something or transfer function as we're about to start, right? We don't need to go through and solve for everything. We can just use the final value theorem and skip ahead to get that, right? And that's going to be relevant later in this class, right? Any questions on this stuff before we move into transfer function review? All good? So transfer functions. That's what our main focus is going to be for today. So let's look at three types of models for dynamic systems. This isn't necessarily all the types of models that we could have, but these are the major ones for controls engineers, I would say. The first one would be state space or state variable, as some textbooks refer to it, models. And what a state space model looks like for a nonlinear system, we have a bunch of our states, x vector here. The rate of change of those is equal to some nonlinear function that depends on our states and any inputs we have. And we also have our outputs, y, which is also dependent on a nonlinear function here. All right. There's also a linear version of this, if our dynamics are linear, where if we have a matrix A, matrix B, that's our input matrix. Then we also have a matrix C for our output matrix, and D, our feed through matrix. We can write that a different way here, right? State space models are n, where n is the number of states that we have, nth order first, I should say, n first order ordinary differential equations, right? So we can see there is no like x double dots in here. There is no x1 dot is equal to x2 dot plus x3 or something like that, right? It's all first order ordinary differential equations, right? We won't use that too much in this class, but that is like a very good standard way of modeling a lot of dynamic systems here. The more vibrations approach is to use nth order differential equations. I'm not as much of a fan of this, but it definitely has its uses in some cases where we have, and we'll start out with the problems for today. If we say we have one input and one output, just for this example, and we have n derivatives with respect to time, all the way down to dy over dt plus a0 times y is equal to, let's say, m derivatives with respect to u. This is another way that we can express the dynamics. This is specifically for single input, single output. Though we could have multi-input, multi-output for this type of system here as well, right? This is another way to represent our systems. Probably you guys have used this a lot when you're trying to model your mass spring damper systems, which we'll cover again in a little bit, right? This is a common way to express those types of dynamics. Okay, and the last one, the one that we'll focus on for the most in this class, is the transfer function. Right. Right, that'll be our focus for today. Right, so a transfer function. Can anybody give me a basic definition of what a transfer function is? Output over input, I would say Laplace transform of the output over the input. Question.
So you can change the layout of the screen then? The process covers.
There we go. Can't promise it won't pop up again. Laplace transform of the output over the input. All right, that's what our transfer function is. And that's our standard way that we're going to be modeling systems in this class. So let's take this nth order differential equation that we had with one input and one output. And let's say this with all initial conditions equal to 0. Technical definition of that would look like D to the, I was using big N, so I'll stick with that. Should be, yeah, it should be dn little n, let's use y over dtn at t is equal to 0 is equal to 0 for n is equal to 0 all the way to n minus 1, right? That's just saying that we don't have any initial conditions for this equation that we had up there, right? We take a Laplace transform. This should be a to the n here. Of everything on both sides. I'm just going to skip down to the a0 times y here. Take a Laplace transform of both sides and then solve for y over u, right? So Laplace transform of a0 times y, that's implied to be y as a function of time. How are we going to write that out in this case? Just a big y of s, right? What about, let's go with the first order one. I didn't write it down here, but dy over dt times a1. What's the Laplace transform of that? How are we going to write that out? S, well, a1 s y of s, right? Right. So then what would be for that nth order one? What would we write for that very first one that we had? Say again. an s to the n, right? All right, we can see a pattern here. If we don't have any initial conditions, just the order of the derivative is how many s's we're going to have, right? To the power of that, right? Same thing on the other side, and this should be times y of s, right? The other side should have bm s to the m times u of s all the way down to b0 times u of s, right? Or s to the 0 power, right? We can group all these terms together, an s to the n plus all the way down to a0, implied that it's a0 s to the 0, right? Multiplied by y of s. Do the same thing over here. And then we just need to divide by this to get y over u, right? And that is our transfer function for this generic case. Right. And usually a transfer function is represented by, I don't know, a t of s, g of s, etc. Anything that's a function of s, right? Transfer function represents our dynamics for this system, right? Notice here, right, that there is no s to the -1, s to the -2, right? There is no 1 over s showing up anywhere like this. We have a what's this called? Like a rational numerator and rational denominator. Is that the right way to describe it, right? Where it's just the power of s to the 0 going upwards, right? Nothing complicated beyond that, right? So we need to make sure that we always try and simplify our transfer function down to this form, or when we have our roots of the numerator and roots of the denominator. A proper transfer function. How many of you guys have heard the term proper transfer function and strictly proper? How many of you have not heard it? Okay, that's fine. So a proper and strictly proper transfer function, they are just different categories of transfer functions. A proper transfer function says that n, the number of derivatives of y, is greater than or equal to m. A strictly proper transfer function says that the number of derivatives of y with respect to time is greater than the number of derivatives of u with respect to time here. That's our difference between these two, right? We don't ever have a case, or we're not going to ever deal with a case where n is less than m. I think that's usually called like a clairvoyant system or something. It means a system where its dynamics can predict the future. Doesn't really make sense physically. All right. These are just two categories for our transfer functions. We're going to be dealing with both proper and strictly proper transfer functions throughout this class. Okay. Any questions? Should still be in review phase here. So let's go through into a basic example. Y dot plus 10y is equal to 12 times u, and y of 0 is equal to 0. Take a minute or two, and then let's have someone from the chat that's online tell me what our transfer function is. So find ys over u of s. I'll give you guys like a minute or so. And if you guys are really fast before we get a response, you'd also get a transfer function for this case. All right, anyone online? Did you get the idea for your transfer function? Okay, folks in class, what we get? All right. 12 over s plus 10 up. A couple people in the chat just got it too. Great, right? It's just sy of s plus 10, y of s is equal to 12 u of s. That one's pretty straightforward. How about for this one? We would still have the same approach, right? Laplace transform of y double dot plus 2y dot plus y is equal to 3 u dot plus 2u. I already said that our initial conditions, our input at the beginning are all 0. So we just do a Laplace transform for each one of these elements individually. There's no real trick here in this one, right? It's pretty straightforward. Without any initial conditions, this will be s squared y of s. This will be 2 times s y of s. This will just be y of s. This will be 3s times u of s. And this will be 2 times u of s, right? We just need to group things together. And then solve for y over u. Right, pretty straightforward. Same as the first case, just a few more steps to it. Okay, now let's move into a slightly different form. Let's say we had a state space model. X1 dot is negative 4x1 plus 2x2. Let's say x1's initial condition is 0. X2 dot is x1 minus 6x2 plus u. X2's initial condition is also 0. And then y is x1 plus x2 plus u. And we still want to find y of s over u of s, find the transfer function for this system, right? Where x1 and x2, if you guys aren't familiar with state space modeling, those are our states. Those are the things that represent potentially energy storage in our system or mass storage potentially, or a variety of different things. They essentially represent the internal dynamics of our system. But we don't need to know too much about that in order to get our transfer function for this case. So, suggestions. How do we go about doing this? I give you this equation here, or this set of equations, and I say find our transfer function. How do we approach it? We're already technically in a form of state space. Okay. What were you gonna say? Yeah, so we could go through and get the like formal state space representation, right? And I'll cover that at the end of this for the generic one. That's going to involve a matrix inversion, which is okay. It's probably easier, at least in coding. But let's just go with the equations that we have right here, right? So getting it into the proper linear state space form, sure, we could do that, right? We said solve for x1 and x2, but we got to do something even before we get there, right? So what we do even before there?
I'm not sure if this is a valid method or not. You take the Laplace of them and then algebraic.
So that's what I'm looking for here. When I say transfer function, I want you guys to immediately think, okay, if I have a dynamic system in the time domain, take a Laplace transform. That should be your first step here. So let's take a Laplace transform of each one of these equations. We're looking for a transfer function. We want to do a Laplace transform at some point. So we get, with 0 initial conditions, Laplace transform of x1 dot is s x of 1 of s. Laplace transform of -4 times x1 is just big x1 times -4. And same thing with this guy over here, right? We apply that same logic. There's our second equation here. Right, but now we have a Laplace transform of u, so that's going to be our big U of s. And then we have our final equation here. Take a Laplace transform of all that stuff. Everything look good up to this point? Yes? No? Yeah, there's no y dot. It's just y, right? Remember that output equation, there's no y dot, so it shouldn't be s times y of s, at least in these state space models, right? Okay, so now we got this. Now I think the suggestion was over there, right? Now we have x1 and x2 that both are going to come into play for y. So we need to figure out what x1 and x2 are in terms of y and u, right? So maybe first we should take these two equations and solve for x1 of s and x2 of s, right? There's a handful of different ways that you could go about doing that, right? What I would recommend, or at least how I did it in my notes, but it really doesn't matter too much, right, I would solve the first equation for x1 in terms of x2, and then plug that into the second equation. So x1 of s is equal to negative 4x1 of s plus 2x2 of s. We could also write that as x1 plus 4x1 is equal to 2x2. You get s plus 4 over here. And then we can solve for x1 in terms of x2. Obviously, there's a lot of ways to go about doing this, right? You could do a matrix inversion as well. But this is just how I want to go through it, just to keep it kind of basic. Then I have that second equation, x2 of s is equal to x1, which I now know to be in terms of x2. Right? I'm going to multiply everything by s plus 4. Just to get that off the bottom there. Right, and then we can solve this for x2 as a function of u. Right, I guess it would be, well, let's be careful about how we do this. So we're going to have s times s plus 4. We're going to move over a negative 2 from this guy, and then plus a 6 times s plus 4. Keep the u on the other side, right? We want to keep that separate. So this should end up being what? S squared plus 4s minus 2 plus 6s plus 24. And x2 of s is s plus 4 times u of s. Right, and this is like 8th grade stuff, 9th grade stuff, right? And we can solve for x2 of s in terms of u of s and s's and the numbers themselves, right? We get what? S squared plus 10s plus 22. Is that right? That looks right. Okay. So now we've solved for x2. And as a result, right, we've also solved for x1. Both in terms of u. Okay. Now what do we do? You speak really quietly. Put it back in to our output equation here, right? And then solve for y over u, right? So our output equation was just x1 plus x2 plus u of s. I'll write it down here. And you guys just tell me what that should end up being for our transfer function. Was it just 1 times u? It was. Anybody get anything? I'm sure you could use some sort of symbolic solver to do this, right? But it may be good to just practice this by hand, or if you have a calculator that can do something like this, maybe not a bad idea. In case you don't have access to a symbolic solver or a computer for an exam, let's say. So what do we end up with? Anybody got anything for y of s over u of s? X1 plus x2. So let's try and write it out here. Y of s is x1, right, which is 2 over s squared plus 10s plus 22, right, times u of s. Then you said x2 as well, right? So we plug that in. I think that's what you're going for here. And then you said just u of itself, right? I'm guessing you just grouped these three things together, right? And called it a day. And that's good. That is technically correct, except you would not get full points from me on an exam if you were to present it in this way. So if you were to write it out like this, well, hold on. You need to combine all three is the key here, right? I don't want a transfer function that's three separate pieces in most cases, right? It'll make analysis a lot more difficult typically, right? Or more time consuming. And I don't want a transfer function where you combine these two and then you have a +1 at the end. That is not a complete transfer function to me. It should be a polynomial on the top, one polynomial for the numerator, one polynomial for the denominator. And that's it, right? So I want this to just be one big fraction, is what I'm asking for. Right? So we can see the denominator is going to be s squared plus 10s plus 22, right? And the numerator will be 2 plus s plus 4 plus 1 times that denominator that we need to multiply by. And what do we end up with when we get that? 28 over s squared plus 10s plus 22, right? This is what I'm looking for typically. And I usually outline problems for the most part saying, I want it to look like a polynomial, or I want you to tell me what each of the terms is in front of each s, right? This is technically s to the 0 here. We just don't write it out, right? So while this answer is correct, technically, right, I need it to be in this proper form here, right? Or the typical form. Okay, good. So in general, since some of you guys mentioned the state space modeling stuff, right? We have a linear state space model. Right, there are multiple ways that we said we could solve the above. One of them would be to do some sort of matrix inversion solution. The transfer function, or the family of transfer functions, if we have multiple inputs and multiple outputs, would be C S times I, the identity matrix, minus A, all that inverted, times B plus D, right? And then you would need to simplify this, right? We have multiple inputs and multiple outputs, right? We're going to have multiple transfer functions, right? That's why these are vectors here. Right, should probably represent as a matrix, really. All right, so that ties into what if we have two inputs? We have two transfer functions. So for our example here, y dot plus 10y is equal to 12. Now it's going to be u1, our first input, plus 3 u2 for our second input here, right? We can't get a transfer function for this on its own. We can get two separate transfer functions because we have one output, but we have two inputs, right? So we would still do the same thing as always. We do a Laplace transform. I'm just going to group the terms on the left together. Right? And then we're going to get two transfer functions. I'll call the first one T1 of S. We're going to set all inputs that, except for the one that we're interested in, equal to 0, just for this time. And then we're going to solve for Y of S. If we were to do this, we'd get the same transfer function we got in our earlier example. So this is U1 now. All right, and we'll call this T1 of S. All right, for T2 of S, our second transfer function, set all inputs except for the second one equal to 0. So Y of S over U2 of S, which we're going to call T2, that's going to be 3 over S plus 10. Notice that both of these still have the same denominator in this case. That may be a pattern that shows up later, right? But typically, we're not going to deal with multiple inputs or multiple outputs in this class, at least until we get to the steady state analysis stuff. Right, and start talking about disturbances in our systems. Then we'll have multiple potential transfer functions. What if you have initial conditions? So what if our initial conditions are non-zero? Can you get a transfer function in those cases? No? Why not? I can't hear you again. You can't group U of S and Y of S together. So I understand where you guys are coming from, where you say that, all right, if we have initial conditions, we can't get a transfer function. I would disagree, right? So something that I covered in my 3333 class, and hopefully you guys may have seen to some element, right, is that initial conditions and inputs are kind of related to each other, right? An impulse input actually just changes your initial conditions. So if you have initial conditions, my argument would be to treat them like inputs. Right? So let's say y dot is equal, or y dot plus 10y is equal to 12u1 plus 3u2, and y of 0 is not equal to 0, right? I'd say the first two transfer functions you would get are normal for the other cases, right? So T1 of S and T2 of S are the same as we set y0 is equal to 0 for those cases, right? Get our transfer function, at least the way you guys have traditionally been taught. You can't have initial conditions, so we set them to 0. But then I would argue that we're going to have a T3 of S set inputs, and in the cases of higher order systems, all the other initial conditions equal to 0. So let's do a Laplace transform of this guy with our inputs equal to 0, but our initial condition is non-zero. What do we end up with in this case? Is this right? Right, we have an initial condition, right? Which I am kind of pretending here to be U3 of S, right? That's the way I view it. And so we can get a third transfer function here. Y of S over that initial condition, which I'm going to call T3 of S, 1 over S plus 10. Now, some control engineers may not view it in this way, right? But I'm trying to show the connection between our inputs and our initial conditions, right? Having inputs can actually change what your initial conditions can be, right? This is actually essentially an impulse response function, what we have here. Okay, do we have any questions on that? Yeah.
So we're finding here
Pretty much, that's what's going on here. we set all other inputs except for the one that we're interested in equal to 0, right? Because a transfer function by definition is one input and one output, right? You cannot have a transfer function with multiple inputs, right? At least for a representation. Notice that in all these equations here, we don't have like U2 of S doesn't show up in here, or U1 of S doesn't show up in here. The initial conditions don't show up in there, right? It should just be Y over U is equal to some sort of parameters multiplied by S's. Question?
Writing out T1. And you need to define
This sounds more like a question, like if you were trying to fill out a homework, is that what you're asking? Right? Or is it like okay, you're probably not going to get homework assignments like this, right? I just want to cover this to make sure you guys understand it. So it would be like for T1 of S, set U2 of S is equal to 0 and Y0 is equal to 0. That's how I would define it, right? Does that answer your question? Yeah. That's how I would say how to do it, right? I wouldn't actually call U of 0 or Y at time is equal to 0 as U3, but if you want to think about that, you can go about that way. Okay, any other questions? All right, so we have one more thing with transfer functions, but I think we can save that for next time since we're running short on time here. All right, so that is it on Friday. We'll go through the remainder of transfer functions, block diagrams, and then get your first homework assignment. Okay, so give me a second. I'm not gonna be able to hear you over all this noise. Folks online, do you have any questions or anything? If not, I'm gonna end the meeting fairly soon. Oh, I think he's first. All right, folks online, I'm gonna end the meeting here.